Welcome everyone. Question number 101. A linear arch or theoretical arch is an imaginary line or funicular polygon representing the exact path of pure compressive force or line of thrust for a specific load distribution. Whereas in contrast, an actual arch is the physical arch constructed usually circular, parabolic or elliptical in shape to accommodate moving loads. Normal thrust only. Option A is right answer. Question number 102. A 3-hinge arch is carrying uniformly distributed load over the entire span. The arch is free from shear force and bending moment if its shape is parabolic. Option B is right answer. Question number 103. For a determinate pin jointed plane frame, the relation between the number of joint J and the members M is given by. For perfect frame, we know the relation M equal to 2J minus 3. M is the number of members in the frame, J is the number of joints in the frame, and if this equation is satisfied, then we will call the frame as a perfect frame. So let's see for a triangle ABC. Number of member equal to 3, number of joint equal to 3. Okay, now if we put the value in this equation is satisfied for this frame, so the triangle can be treated as a perfect frame. Option A is right answer. M equal to 2J minus 3. Number 104. In the pin jointed plane frame shown in the figure 10.5, the force in the member BD is. First we have to know the zero force member rules in a truss in a plane frame. Number 1, if in a truss 3 members meet at a joint where 2 are collinear and joint is subjected to no loading, the force in the non-collinear member is 0. And number 2, at a joint subjected to no loading, if 2 non-collinear members meet, then force in both members is 0. So in this frame, in this truss, we have to determine the force in the member BD. Okay, so suppose at this joint D there is no loading. Okay, and 2 collinear members are AD and DC. Okay, so by the rule 1, these 3 members BD, AD, DC meet at this joint D. Okay, the force in the non-collinear member, that is BD, is 0. Option D is right answer. Question number 105. The basic perfect frame is a triangle. Option A is right answer. Question number 106. Method of joint is applicable when the number of unknown forces at the joint under consideration is not more than 2. Option B is right answer. 107. Force in the member AD of the pin jointed frame shown in the figure 10.6 is. By zero force member rules, force in the member AB and force in the member BC is equal to 0, because at this joint, that is at B, there is no loading and the force is force and by the zero force member rule, the force in both the member is equal to 0. So if AB equal to FBC equal to 0. Now force in the member AC, that is diagonal member, balances the diagonal load P. Force in the member AC balances the diagonal force P for equilibrium, and they are collinear and no force is required at the vertical member AD. Option A is right answer. Question number 108. The rigid jointed plane frame shown in the figure 10.7 we know the formula for column stiffness K equal to 12 EI by L cube. Okay, this is our fundamental equation. So if the column is long, the stiffness will be less. Okay, so for this column the stiffness will be less. Okay, as the stiffness is less, the frame will move at that side and sway will take at this place, at the right place. Okay, at the right side. Way to the right. Option A is right answer. Question number 109. A hollow shaft will transmit more power than a solid shaft of the same weight and material. Option C is right answer. This is because in case of hollow shaft, more material is distributed away from the center, maximizing resistance to twisting. Question number 110. The stiffness of a helical spring is expressed as load per unit deflection. Option B is right answer. Number 111. The ratio of maximum shear stress developed in a solid shaft of diameter capital D and a hollow shaft of external diameter capital D and internal diameter small d for the same torque is given by, as given, solid shaft dia equal to capital D and hollow shaft external dia capital D and internal dia small d. Okay, and both the shaft is subjected to same torque. Okay, We know the formula for shear stress in the shaft, tau equal to Tr divided by J. J is the polar moment of inertia of the shaft, R is the radius of the shaft, and capital T is the torque to which the shaft is subjected. For solid circular shaft, polar moment of inertia Z dash will be equal to pi d to the power 4 by 32, and radius Rs will be equal to capital D by 2, and shear stress tau s will be 16T by pi d cube. And for hollow circular shaft, the polar moment of inertia JH will be pi d to the power 4 minus small d to the power 4 by 32, and the RH will be capital D by 2, and shear stress tau h will be 16T capital D divided by pi into capital D to the power 4 minus small d to the power 4. Okay, now if we make the ratio tau s by tau h, then we will get the value capital D to the power 4 minus small d to the power 4 divided by capital D to the power 4. C is right answer. 112. If a shaft of diameter small d is subjected to a torque capital T, the maximum shear stress is 16T by pi d cube. Option C is right answer. Question number 113. In a rectangular shaft subjected to torsion, the maximum shear stress occurs at the middle of the longer side. Option D is right answer. Question number 114. A solid circular shaft of 6 meter length is built in at its ends and is subjected to an extremely applied torque 60 kN meter at a distance of 2 meter from left end. The reactive torque at the left end and the right end are respectively. So reactive torque at the left end will be TB divided by A plus B. So A is equal to 2 meter and B is equal to 4 meter, and torque given in the question is equal to 60 kN meter. So if we calculate TL, the reactive torque at the left end will be 40 kN meter, and reactive torque at the right end will be TR equal to TA divided by A plus B. That means 60 into 2 divided by 6 equal to 20 kN meter. Option B is right answer. Number 115. The ratio of strain energy stored by a hollow shaft of external diameter capital D and internal diameter small d, and strain energy stored by a solid shaft of diameter capital D is. We know the formula for strain energy for solid shaft. US equal to tau square by 4G into V. V is the volume of the shaft, tau is the shear stress of the shaft, and capital G is the modulus of rigidity of the shaft. And strain energy for hollow shaft UH will be equal to tau square by 4G into V into capital D square plus small d square by capital D square. Capital D is the external diameter of this shaft and small d is the internal diameter of the hollow shaft. Okay, so if we make the ratio UH by US, then we will get the value capital D square plus D square by capital D square. Option A is right answer. Number 116. If the internal radius of a hollow shaft is n times the external radius, then the ratio of the torque carried by the hollow shaft and solid shaft of same cross-sectional area and subjected to same maximum shearing stress is. Suppose external radius of the hollow shaft is equal to capital R and internal radius of the hollow shaft equal to n times the external radius, so n capital R, and radius of the equivalent solid shaft is equal to small r. Now they have same cross-sectional area, so we can equate the area of hollow shaft is equal to area of solid shaft. So pi small r square equal to pi capital R square minus n square r square. Pi r square is the cross-sectional area of the solid shaft, and this equation is the cross-sectional area of the hollow shaft. Okay, so by calculating small r will be equal to capital R into root over 1 minus n square. We know the value of torque of this shaft T equal to capital T equal to tau into J divided by capital R. R is the radius of the shaft, tau is the shear stress, and J is the polar moment of inertia. So for hollow circular shaft, polar moment of inertia will be pi by 2 into capital R to the power 4 minus small n to the power 4 into r to the power 4. And if we simplify, that will be equal to pi by 2 into r to the power 4 into 1 minus n to the power 4. And the torque TH will be equal to tau into JH by RH. JH is the polar moment of inertia of the hollow shaft, and RH is the radius of the hollow shaft. If we put the value of JH equal to this in this equation, we will get TH equal to this value, that is equation number 1. And for solid circular shaft, the polar moment of inertia Zs will be equal to pi by 2 into r to the power 4, and torque Ts will be equal to tau into Js by Rs. And if we put the value of Js into this equation, we will get Ts will be equal to pi into tau into r cube by 2. This is equation number 2. So if we make the ratio Th, torque at hollow shaft, divided by Ts, torque at circular solid shaft, then we will get the ratio by putting the value of small r is equal to capital R into 1 minus root over of 1 minus n square. We will get the ratio is equal to 1 minus n to the power 4 divided by 1 minus n square into 3 by 2. And if we simplify, the ratio will be equal to 1 plus n square divided by root over of 1 minus n square. Option D is right answer. Number 117. If a circular shaft is subjected to a torque capital T and bending moment capital M, the ratio of maximum bending stress and maximum shear stress is. We know the formula for bending stress is equal to 32 m divided by pi d cube, and shear stress is equal to 16t by pi small d cube, pi d cube. D is the diameter of the shaft, m is the bending moment to which the shaft is subjected, and T is the torque to which the shaft is subjected. Okay, now if we make the ratio between bending stress divided by shear stress, the ratio will be equal to 2m by T. Option A is right answer. 118. If a shaft of diameter small d is subjected to a torque capital T and bending moment capital M, the maximum shear stress is. We know the formula for a maximum shear stress for a solid circular shaft. Tau max is equal to 16te divided by pi d cube. D is the diameter of the shaft. Te is the equivalent torque, which is equal to root over of m square plus t square. T is the torque to which the shaft is subjected, and m is the bending moment to which the shaft is subjected. So T equivalent will be equal to this. So if we put T is equal to this value in this equation, we will get tau max is equal to 16 into root over of m square plus t square by pi d cube. Option B is right answer. Question number 119. The radius of gyration of a circle of radius capital R is equal to. Radius of gyration value is equal to capital D by 4, and D means 2R. So if we want to get it in terms of radius, then it will be equal to capital R by 2, where capital D is equal to 2R. Capital D is the diameter and capital R is the radius. And B is right answer. Question number 120. A masonry pier ABCD shown in the figure 10.8 supports a vertical load W at a point P. Thus, nature of bending stress at A due to eccentricity of the load about x-axis and y axis respectively are. So, if we consider the masonry pier ABCD, okay, and consider the stress about x-axis due to eccentricity, the point P is located in the upper half of the section, positive y direction relative to x-axis. Okay, the load W at the point P creates a moment about x-axis that tends to compress the top half of the pier, that is AB, okay, and create tension at the bottom half, that is CD part. Okay, so nature of bending stress at A at the upper half of the pier will be compressive stress. Okay, and if we consider the stress about y axis due to eccentricity, the point P is located in the right half of the section, that is y section, positive x direction relative to y axis. The load at this point P creates a moment about y axis which compresses the right side, that is B and C, okay, and create tension on the left side, that is A and D. Okay, so nature of stress will be tensile at point A. So option C is the right answer. Number 121. A short column of external diameter of 250 mm and internal diameter of 150 mm carries an eccentric load of 1000 kN. The greatest eccentricity which the load can have without producing tension anywhere is. The formula for greatest eccentricity without having tension on column E equal to capital A y divided by I, and this value E for circular section column will be equal to E equal to capital D square plus small d square divided by 8 capital D. 8 into capital D. Capital D is the external diameter of the circular column, small d is the internal diameter of the circular column, and E is the load. So if we put all the value in this equation, the value of eccentricity E will be equal to 42.5 mm without producing tension on the column. Then D is right answer. 1 to 2. The core of a rectangular section with sides B and D is A. So as shown in the figure, A, B, C, D, this is the core of the rectangular section. Okay, the dimension of the rectangular section, small b is the longer dimension of the section and small d is the smaller dimension of the section, and the distance BD is equal to small b by 3 and distance AC is equal to small d by 3. So this core is a rhombus, okay, with side AB, BC, CD and AD. All the side is same. Okay, so suppose for a side AB, its length will be equal to half of BD, that means OB, and half of AC, that means OA. So half of OB will be equal to B by 6 and half of AC will be equal to OA, that is equal to B capital small d by 6. So AB is the hypotenuse, so AB will be equal to root over of capital small b by 6 square plus small d by 6 square, and if we calculate the final value, AB will be equal to root over b square plus d square divided by 6. Then B is right answer. Question number 1, 2, 3. A reinforced cement concrete footing as shown in the figure 10.9 carries a concentrated load at P so as to produce maximum bending stress due to eccentricities about x-axis and y-axis as 100 kN per meter square and 150 kN per meter square respectively. If the direct stress due to loading is 175 kN per meter square compressive the bend, then the intensity of resultant stress at the corner B will be. So as shown in the figure, A, B, C, D reinforced cement concrete footing, okay, where load P is acting at here, eccentric load. So we have to determine the resultant stress at B. So given at here, resultant stress at A is equal to sigma D plus sigma XX plus sigma YY. Sigma D is the direct compressive stress, sigma xx is the bending stress about x-axis, and sigma yy is the bending stress about the y-axis. So resultant stress at A will be equal to sigma d plus sigma xx plus sigma yy, and resultant stress at B will be equal to sigma d plus sigma xx minus sigma yy, and resultant stress at C will be sigma d minus sigma xx minus sigma yy, and resultant stress at D will be equal to sigma D minus sigma xx plus sigma yy. So by this relations, the resultant stress at the B will be equal to sigma D plus sigma xx minus sigma yy. We have got the value of sigma D equal to 175 kN per meter square, sigma xx is equal to 100 kN per meter square, and sigma yy equal to 150 kN per meter square. If we put all the value at this equation and calculate sigma RB, intensity of stress at B will be equal to 125 kN per meter square. Option B is right answer. Question number 1 to 4. The ratio of intensity of stress in case of a suddenly applied load to that in case of a gradually applied load is, we know the value of stress is equal to load divided by the cross sectional area, okay, but for gradually applied load the load will be average, okay, p by 2, 0 plus p by 2, but the cross sectional area will be same, so the corresponding stress will be p by 2a, but in case of suddenly applied load the stress value will be directly p by a. Okay, so if we compare ratio of intensity of stress in case of suddenly applied load to that in case of a gradually applied load, then the value will be equal to 2. C is right answer. Question number 1 to 5. Proof resilience is the maximum energy stored at elastic limit. Option B is right answer. Proof resilience is the maximum amount of strain energy that a material or body can absorb without permanent deformation up to elastic limit.